Section 6.4 and 6.5 exponential and logarithmic functions is what this section is about. So logarithmic functions are actually the inverse of exponential functions. So that's what we're going to start with. The inverse of the exponential function is the logarithmic function. So the exponential function has this form, y or f of x is equal to a to the x, and a has to be greater than 0. That keeps things from oscillating back and forth. And a cannot equal 1. If a was equal to 1, we would actually just have a constant function. So the inverse of the exponential function, remember when we find inverses, what we do, we switch the x and the y's around. And so we switch the x and the y's around to a still greater than 0, a cannot equal 1. But usually we try to solve for y. Well, when we try to solve for y here, without the logarithmic function, we actually would not have a way of solving for y. So the way we write this, we introduce this new function. It's log base a of x. That way we have things in terms of x is equal to y. And what logarithms are, logarithms actually give us the exponent. It's the exponent to get from a. So it's the exponent to get from a to x. If I want to know what power it takes to get from a to x, so a to x, I go a to the y is equal to x. And that's actually how I kind of remember these a little bit with this circular pattern. Whenever I see logs, I think a to the y is equal to the x. Formally, the logarithmic function with base a, where a is greater than 0 and a does not equal 1. Here's our base. That base is going to be greater than 0. And that's true of all logarithmic functions, that a is always going to be greater than 0 and cannot be 1. Is read as y is the logarithm with base a of x, and is defined by y is equal to log base a of x if and only if x is equal to a to the y. So that's where we had that inverse when we switched the x's and the y's. The domain of the logarithmic function is x has to be greater than 0. Just taking a few statements and changing them into logarithmic form. If we have this 1.5 to the 4th is equal to m and we needed to change it to logarithmic form, we'd have log. I think of that circular pattern, it's 1.5 to the 4th power is equal to m. So we have 1.5 to the 4th, 1.5 to the 4th gives us m, that kind of circular pattern. Here we'd have the log, it's e to the h gives us 25. So we have log base e of 25 is equal to h. Now something I can say about this, base e is considered the natural logarithm. So what we would actually do, we would write ln of 25 is equal to h. Natural logarithm comes from e, which is that continuous growth number, and or exponential number. And so it's so common that we use ln, and ln, even though we never write it there, we just assume that there's a little base e there. We never actually write it, but that's what we assume is there. So then taking a logarithmic and changing it to an exponential, here we have log base a of 3 is equal to 6. In exponential, that's equivalent to a to the 6th power is equal to 3. Log base e of k is equal to negative 2. That's equivalent to e to the negative 2 is equal to k. And this one right here, normally the way we would see this one, because it's so common, is we'd see ln of k is equal to negative 2. If you see that ln, you just can assume automatically that it's base e. And so we never actually write it there, but that's really what's there. Finding some exact values of these things, when you see log base 2 of 8, what this is saying is 2 to what power would give us 8? Well, 2 to the 3rd gives us 8, so log base 2 of 8 is equal to 3. Another way of thinking of this, log base 2 of 2 to the third. Well, 2 to get to 2 to the third, we would need 3. Log base 5 of 25. 5 to what would be 25? Well, that's 5 to the second. So log base 5 of 25 is equal to 2. The domain and range of logarithmic functions. If you think back to the exponential function, so the exponential function was some a to an x power. That was the exponential. So on the exponential function, we had a domain, negative infinity to positive infinity. Well, the inverse takes the range, which was 0 to infinity, and it moves it back to the domain. So what happens with inverses, the domain and the range switches. The domain of the exponential was negative infinity to positive infinity. That's now going to be the range of the logarithmic, and the domain of the logarithmic is the range of the exponential, or 0 to infinity. So whenever you see a log, unless there's some sort of shift or something, the domain is from 0 to infinity. In this case, we'd have an interval notation, 0 to infinity, and the range is from negative infinity to positive infinity. So looking at some of these in practice, how do we end up finding the domains? Well, what log base 4 of x plus 1 over x minus 1, this x plus 1 over x minus 1, we know that that has to be greater than 0. And from our experience with rational expressions, we also know that this bottom here can't be 0. So we also know that x minus 1 cannot equal 0. So one of our restrictions, x cannot be 1 if I solve for this. And then this part here, this has to be greater than 0. Well, where does that happen? If I think back graphically, x plus 1 over x minus 1, I look at the numbers in front of the x's, they have the same power. So they're going to have a horizontal asymptote at y equals 1. The vertical asymptotes where the bottom can't equal. So the vertical asymptote is at x equals 1. It's going to equal 0 when x is negative 1, right there. And so our graph is going to look something like this of what's inside the logarithm. Well, where is this greater than 0? It's greater than 0 on this interval and this interval. So this here is greater than 0 from negative infinity up to here, which is negative 1, or from 1, it has to be greater than 1, up to positive infinity, like that. How about this one down here? So this one down here again, what's inside the logarithm has to be greater than 0. If I go back a slide, the domain, what's inside the logarithm has to be greater than 0. So what's inside here, the x plus 3, has to be greater than 0. X has to be greater than negative 3. Our domain in interval notation is from negative 3 to infinity. Graphing the logarithmic function, looking at some properties here. This right here, when you're looking at this particular graph, this is actually when a is between 0 and 1. So again, as you're looking at this graph, this one would be where a would be between 0 and 1. So log the base here, the base is between 0 and 1. The domain is the set of positive real numbers, or 0 to infinity. Notice how this graph of this logarithmic, in this case we have y is equal to a to the x. This was the exponential, and then the logarithm is the inverse. this inverse, or this log, is never actually going to go farther than the x equals 0 line, the y-axis. The domain is from 0 to infinity. The range starts high, very, very high, keeps on going down low, so negative infinity to positive infinity. The x-intercept is 1, 0. That's always going to be true. So log base anything of 0, if I put 0 in for x, to get from something to power to get to, when I put in 1 for x, to get from something raised to power to get to 1, it's always going to have to be 0. So the x-intercept, to get up or down, neither high nor low, to get out 0, we'd have to put 1 in for x. That's always going to be true no matter what this base is. There is no y-intercept. It never crosses the y-axis. That's because the y-axis is a vertical asymptote of the graph. The logarithmic function is decreasing if a is between 0 and 1. So like I was saying, this one is going down. That's because a is between 0 and 1. It would be increasing if a is greater than 1. So if the number in the logarithm, the base, is greater than 1, then it actually looks something more like this, if a is greater than 1. The graph is going to contain the points 1, 0, a1, and 1 over a negative 1, and the graph is smooth and continuous and with no corners and gaps. So this just keeps on going nice and smooth. The natural logarithm. Notice how I said on the previous slide, if a is greater than 1, then we get something that looks like this. Well, in this case, y is equal to the natural log of x. ln, we never write it there, but it's base e. And e is approximately 2. It's slipping my mind now. 2.72, I think, is approximately what e is. So notice the base here is greater than 1 if it's e, and so we get this type of shape right here. So if y is equal to e to the x, then the inverse is going to look like this. And keep in mind, inverses reflect over the line y equals x, so that's reflected, or it's folded over the line y equals x. The common logarithm, this is another one that's very, very common. So if you look at your calculator, all you're going to see is a log button. It doesn't have a number down there. That's because it's considered the common one, which is base 10, kind of like you have 10 fingers or toes. If you see a common logarithm with 10, we usually never write it there. We just put log x. And so this, again, when that base, we never write a 10 there. If it's a common logarithm, but if that base is base 10, we would get this right here. So doing some practice with these, let's say log base of x of 81 is equal to 2. What that's saying is x to what power? So to the second power is equal to 81. Well, what number squared is 81? If we square root both sides, we'd get x is equal. You might remember me saying before, you may have to make sure to plus or minus, so we'd get plus or minus 9. However, think back to the restrictions. Here, this base, so we don't get some oscillating thing, this base here has to be a positive, so we're going to forget about the minus here and just do x is equal to 9. In this case here, this is saying e to some power is equal to x, but this ln, this is a common one. It's base e. This is one that you would have on your calculator. All you would have to do on this one is type in ln of 5, and you would get 1.61 for x. Now you might be thinking, well, you don't give us a calculator on a test. I would have to not let you calculate this basically on a test. But know that that button there is on your calculator, ln of 5. So you could do ln, type in a 5, and you get 1.61 approximately. some properties of logarithms, some things that really help us simplify stuff. And it might not look like it at first, but the more comfortable you get with these, the more you realize that this really does help us simplify. So one of the properties, log base a of 1 is always equal to 0. So anytime you see here, anytime you see a 1, you can always think it's going to equal 0. Log base a of a is equal to 1. That's because a to what power would give you a? Well, that's a to the first gives you a. And right down here, you can pause this and look at these parts for yourself. These are just showing you why these two first properties exist. So in the properties given next, m and a are positive real numbers, and a cannot equal 1. R is any real number. The number log base a of m is the exponent to which a must be raised to obtain n. Well, all that is there to show you, or as necessary requirements, but the necessary requirements, as long as those are met, which they usually are, is saying if you have something, so a base, raised to a log with that same base, logs are inverses. So if you take a base, raise it to a log with that same base, it's an inverse. So it's going to undo itself, and you're going to be left with what's inside, the m. So 5 to the log base 5 of 7. Well, this is an inverse, so it's just going to be, this part kind of undoes itself and you're left with 7. The logarithm with base a of a raised to a power equals that power. Again, log base a of a, so logs are inverses. If you have a, the base a, and a to the r, they're going to kind of undo each other, and you're going to be left with that a, or that r. Some more properties of the logarithm. The first one is the product property, or the log of a product equals the sum of the logs. If you see a product, two things getting multiplied together inside a logarithm, it's the same thing as the individual logs, except with an addition sign between them. So we would take the log base a of the first product, or the first factor, that's what this is, plus the log of base a of that second factor. The log of a quotient equals the difference of the logs. If you have the log of a fraction, it's the log of the top minus the log of the bottom. That's how I think of it. Log of the top minus the log of the bottom. If you have log base a of m to the r, so if you have a log of something to a power, that power can get moved out front. So you just have log base a of m. And this bottom one, a to the r is equals e to the r ln of a. What's that is saying is that you can change an exponential into something involving logarithms. And here's kind of a short explanation for how that works. If you look at this right here, this would really be e to the ln of a raised to the r times the ln of a, power raised to power, get multiplied. Well, this right here is just the inverse of itself. So where this really comes from is a to the r, which is that right there, but you change this into this, and then you're going to get e to the r ln of a. So something with a base of e. Here we have something where it says find the exact value of the expression. How we're going to do this is using some of these properties of the logarithm. The property in this case, I see a plus between them, so the property I want to use is the sum of the logs right there. I'm going to go backwards from having two separate logs getting added together to having one log. I can do that because they have the same base, base 6, of 9 times 4. 9 times 4, log base 6 of 9 times 4 is log of 36. Well, 6 to what power gives us 36? That's 2. 6 to the second gives us 36. So all said and done, this equals just 2. Trying to use these properties to expand some stuff and then simplify. Here we have log base 3 of 27x. We have the log of a product. To have a log of a product, we can have two individual logs where we have the factors in between. So we have a product, changes to addition with the properties of logs and x. Log base 3 of 27, 3, can I simplify this? 3 to what power would give us 27? Well, that's 3 to the third. 3 to the third is 27, so that this one simplifies to just 3, and then plus log base 3 of x. It would be that one. Expression as a sum or difference of the logarithms. This one here, ln of e to the x. Again, we have that product right in there. So this is ln of e and ln of x with addition between them. Ln of e, you could think of that like e to the first. The ln has a base e. We never actually write it there. I just put it there to remind you that it's there. These here are the inverses of each other, so we end up with 1 plus ln of x. Here, this one gets a little bit longer, but still doable. Here we have a quotient. We have something over top of something else. So that's log base 5 of cube root of x squared plus 1. That's the log of the top minus the log of the bottom, x squared minus 1. When I look at that second log, there's no multiplication inside there, and there's no quotient, there's no power. The second part right here, this part's done. But the first part, the cube root, that would be like having log base 5 of x squared plus 1 to the 1/3 power. We have a power there, so that power is going to go out front. That power goes out front. So the 1/3 is going to go out front. 1/3 log base 5 of x squared plus 1, and then the other stuff, the minus log base 5 of x squared minus 1. And that would be that one expanded using some of those properties. This one here, write this expression as a sum or difference. Well, we got the same thing. First I see a quotient inside here. Notice that we have this restriction here so that we don't end up with 0 in the bottom. But here we have the log of the top, the x cubed square root x plus 1 minus the log of the bottom, x minus 2 squared. In this first one, now I have a product here because I have x to the third times the square root of x plus 1. So that's the product. The log of x to the third plus the log of a square root of x plus 1 minus, here I have a power. That power can go out in front, log of x minus 2. Here I have a power. That power can go out front, log 3 log of x plus, if I want to think of the square root as a power, I can do that. It's the power of 1/2 minus 2 log of x minus 2. So we have 3 log of x plus that 1/2, that's a power again, that can go out front. So 1/2 log of x plus 1 minus 2 log of x minus 2. And that would be expanded as far as we can, because now there's no more products, no more quotients, and no more powers. These logarithms, they take a little bit to get used to, but once you get used to, they really do help solve a lot of stuff. And I will add that there's probably somewhere in the range of an exponential amount of logarithm jokes out there. Good luck!